Hello AP Physics students, this is Dr. Brenzi and this is lesson 8.1.1. We're starting a brand new unit and this unit is going to be about what's called fluid dynamics. So we're going to be dealing with what are called fluids, and in physics a fluid is anything that's either a gas or a liquid. So our objective for this lesson is that we're going to be able to explain the physics behind pressure and density. So I'm going to go over those two terms and then we're going to calculate these quantities in fluids. All right. Well, let's start off with density. So density is defined as the mass per unit volume of an object. So it's in a way to measure the amount of matter that you have in a unit amount of volume. We usually use the variable rho, which actually looks more like a P than an R, but that's the Greek letter rho. And if you want to find the density of an object, you take the mass and you divide that by the amount of volume in it. And the units of that density are kilograms per cubic meter. Now another way that is common to express density is to actually compare the density of the object to the density of water at 4 degrees Celsius. Now we have to specify the temperature because the density of water actually changes with temperature. So you have to specifically say at 4.0 degrees Celsius. So when we do this comparison, we take this ratio of density over the density of H2O. Then we get something called specific gravity. So you'll need to know that as well. So if you run into what specific gravity is, it's just like a ratio of density to the density of water at 4 degrees Celsius. Okay, now let's talk about what pressure is. So a fluid, which is liquid or gas, at rest exerts a force perpendicular to any surface it's in contact with. So in this diagram, you see arrows going up, you'll see arrows going to the left, arrows going down, and arrows going to the right. Well, that is the fluid exerting a force perpendicular to all of the surfaces that it's in contact with. Pressure is the amount of force exerted by the fluid per unit area. So if we were to take a little bit of area off of this wall right here, and if I were to blow it up, okay, if we're speaking about calculus, we would call this infinitesimal area, we would call it dA. And acting on that is a force, dF perpendicular, okay, because it has to be perpendicular to the area. And so that we would say that pressure is equal to dF dA. Okay, so it is the derivative of perpendicular force with respect to area. So if you have a liquid that is exerting a force, a uniform force everywhere, then you would say that the pressure of that fluid is constant. But sometimes perpendicular force can actually change at different areas, and so sometimes pressure is actually not constant. Now pressure, unlike force, is exerted in all directions in the fluid, so we can't say that it has a particular direction, so we actually have to call it a scalar. The units of pressure are what are in terms of 1 Newton per meter squared, right? We have a unit of force divided by a unit of area. You might recognize that when we're talking about stress and strain because that is the same unit of measurement. 1 Newton per square meter is 1 Pascal. So the unit of pressure is the same as the unit of stress that we learned in our last unit. There's another common unit of measurement for pressure, and that's called an atmosphere. It's the pressure that air exerts on everything around it at a temperature of, I believe, 20 degrees Celsius, which is approximately room temperature, at sea level. Now, I'll tell you why it has to be at sea level. But 1 atmosphere which is the pressure at sea level in a room, typical room temperature, is 101.3 kilopascals. Don't forget that K there. It's really important. Okay, another thing that is very common when talking about pressure is to actually talk about gauge pressure, and we then have to compare that to absolute pressure. Now this is very common in, say, like tires or other inflatable objects. Anytime you are trying to put compressed air or take compressed air or take air out of something, you talk about gauge pressure. So the gauge pressure is the inside pressure of your fluid minus the pressure outside of that container. So if we have a flat tire, we have a gauge pressure of 0 pascals because the pressure of the air inside the tire is the same as the pressure of the air outside the tire. So the air inside is exerting no net, or the air is exerting no net force on the sides of the tire. However, if we compare that to a tire that's inflated, you might get a gauge pressure of what's called 210 kilopascals. Or actually, that's just an example. And the reason behind that is because the air inside actually has an absolute pressure of 311 kilopascals. So it's exerting a force per unit area on the inside of the walls of the tire of 311 kilopascals, but the air outside is exerting a pressure of 101 kilopascals. So the gauge pressure that you would measure is the pressure from the gas inside minus the pressure of the gas outside. Now when you go to actually measure your tires in your tire's pressure level, you are actually measuring what's called the gauge pressure. You're actually comparing the amount of pressure inside to the amount of pressure outside, and you're kind of wondering, well, why is that? Especially since I have a needle that can only sample the air inside the tire. Well, it turns out that that little gauge, if you've ever had a tire gauge, what it's doing is it's pushing on a little tab that comes out of the gauge, and it pushes on that until that force pushing out from the inside of the tire matches the force of pushing back inside from the outside air. So your gauge, your tire gauge, is actually measuring gauge pressure, not absolute pressure. Okay, so let's talk about pressure versus depth. You might remember that when I was talking about defining an atmosphere of pressure, I told you that I had to define that at sea level. Well, why in the world did I have to define it at sea level? Why not define it at the Mile High City, which is 5,280 feet? Well, we have to pick a height, an elevation for our standard unit of our standard atmosphere, and here's why. It turns out that pressure changes with the depth of a fluid. Okay, so the deeper you go, it turns out that there is more pressure the deeper you go inside a fluid. And let me show you why. So let's say here that we have an element of fluid with a mass dm, and we're going to say that that rests inside rests inside it's like sitting inside, a fluid that's, like its own, but we're just taking a little chunk of it, an element. We're going to call the thickness of this fluid element, we're going to call that thickness dy. Okay, we're going to give it an area A, So this cross-section area right here, we're going to call that A. Okay. Now this fluid, this element of fluid has forces pushing on it. Of course it has force due to gravity, so let's write that. So we have gravity pushing down, and that force due to gravity for this element of fluid is Fg, which of course we know is mass times g in the negative direction. But our mass for this little fluid element is going to be dm. So I'm going to say that this is equal to negative g times dm. Well, if I don't want this little element of fluid to fall down or to keep falling, which, in a liquid or a gas it doesn't, then there has to be some sort of force that is pushing it up to balance this gravitational force so that the fluid this little element of fluid can stay in equilibrium. Well, what is the source of that force? Well, it turns out that there is a difference in pressure between the bottom of this element and the top of this element. That's the only way that we can keep this element of fluid in equilibrium. So we have a force pushing down on the fluid. Of course, we have so we know that force is equal to pressure times area, so let's write this as P times A. But underneath, we have to have a little bit more pressure so that the net force is pointing up. So we're going to call this P plus dP. And of course I have to multiply that times area in order to get force. So if I were to write out F net and set that equal to 0 because we are in equilibrium, or actually the way I put it in last unit, let's be consistent, is that the sum of the forces equals 0. So let's do it that way. Sum of the forces equals 0. So I have, first of all, negative g times dm. And then the difference in pressure, well actually, let me just go ahead and write both of these out. So I have P times A pushing down, so I have negative PA. That's the pressure, the force from this pressure on top. And then I have the force from this pressure on bottom. That is going to be plus P plus dP times A. Well, if I were to use the distributive property and multiply this out, you hopefully can see right away that this P times A is going to add out with this P, negative P times A. So now we have negative G dm plus, I'll put that in another color, so plus dP times A is equal to 0. Well, that means that dP times A, and now I'm going to put the A in front, which I should have done last time, but I didn't. So A times dP is equal to G times dm. Now, dm is the mass of this element, And the mass of this element is equal to its density times its volume. So I'm going to write density, rho. So I have negative g times rho. And then I have to multiply it times its volume, which is A times dy. So now I have A times dP is equal to negative g times rho times A dy. Well, I have A on both sides, so this becomes dP equals negative g times rho times dy. Okay. Now usually what happens is then you integrate, or you take the antiderivative on both sides, and you will get so if I were to take the antiderivative of this, and let's say I take it from a pressure 1 to a pressure 2, that is going to equal negative g rho dy, and I have to integrate that from a height from, let's say, h1 to h2. Okay. So, when I do that, I have P2 minus P1 is equal to negative. Now, usually we put rho first, rho times g, times height, h2 minus h1. Okay. So what does this mean? It means that as you climb higher, okay, in other words, h2 minus h1 is positive, that means that P2 minus P1 is negative. Let me pull out another. Slide here. Oops. Yeah, I don't want that slide. Here we go. Okay. So I have P2 minus P1 is equal to, negative rho times g times h2 minus h1. Okay, so if I am at a height h1, let's say that that's sea level. So let's actually make that sea level. Then I have at that place, we have a pressure P1. Okay, so at sea level, the air pressure is P1. But if I were to go to a bigger height, H2, so if I were to go up to the Mile High City with the mountains, right? Welcome to Denver. Now, H2 minus H1 is positive, which means that this quantity on the left-hand side is negative, right? Because I have a negative sign here. So I have P2 minus P1 is negative. That means P2 minus P1 is less than 0, which means that P2 is less than P1. So if you go up to the Mile High City, where the air pressure is P2, that air pressure is actually going to be less than it is at sea level. Okay. Another consequence is that if you are diving in an ocean, let's say that this is the surface of the ocean, well, what's going to happen to that water pressure as you increase the depth? As you go farther and farther down, the pressure of that water is going to increase. And that's why submarines get crushed if they go to a certain depth, because they can no longer withstand the forces due to the very, very large water pressure exerted on the outside of the submarine. We're going to use this equation in class tomorrow. We're going to be using it a lot. Sometimes this is written as delta P is equal to negative rho times G times delta H. So that's a hugely important equation right there. Okay, we're going to be using that equation tomorrow in class, and I will look forward to seeing you then. Bye.